Hey guys, welcome to your last chapter, last lesson, last quiz, last lab, last test in statistics. So exciting. So we are looking at the chi-square distribution. So a few things about the chi-square. You're going to use it for qualitative data. So things that you can put into categories. This is the notation that you're going to use for chi-square, so that makes sense, chi-square. And this notation represents degrees of freedom. So your calculator will give you degrees of freedom, but it's also going to be the number of categories that you have minus 1. Also, your mean is going to equal your degrees of freedom. Your population standard deviation will be the square root of 2 times your degrees of freedom. So, for instance, if your degrees of freedom were 1,000, then that means that your n has to be 1 more than that, 1,001, and your mu would be the same. Your standard deviation would be 2 times that 1,000 and then the square root of that. So the notation that we could use for that would look like this. So a few other things. The curve is going to be non-symmetrical and it's going to be pulled or skewed to the right. There is a different chi-square curve for each degree of freedom that you have. The test statistic for any test is always greater than or equal to 0. And if your degrees of freedom are larger than 90, then your chi-square is going to approximate a normal. So that's that bell-shaped curve. And the mean is going to be just a little bit to the right of the peak on the graph. All right, so we're going to look at two different tests for chi-squared. The first one is going to be a goodness of fit test. And in this type of hypothesis test, you're going to figure out whether the data fits the particular distribution that you're working with or not. So you may think that the data fits a binomial distribution, and you can use a chi-square test and use hypothesis testing to determine if it fits or not. The null and alternate hypothesis are going to be written in sentences, or you can also write them as equations or inequalities like we've been doing. Okay, so here's what we're talking about with the goodness of fit test statistic. This O is going to be the observed value. That's the data that they give you. E is going to be the expected value. So that's like if you roll a die, you would expect it to land on 5 1 out of 6 times. If you flip a coin, you would expect it to land on heads 1 out of 2 times, right? So that's your expected value. And then K is the number of different data cells or categories. So we're going to compute this, and then the sigma tells me that we're going to add all of those up. So the observed values are the data values, and the expected values are the values you would get if the null hypothesis were true. So the expected value for each of our cells has to be 5 or more if we're going to use this test. And as we've already said, your degrees of freedom are just going to be the number of categories minus 1, and your calculator is going to give you that. The goodness of fit test is almost always right-tailed, and for all of our examples and homework problems and lab questions and all of that, we will always use right-tailed. So employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences, and the results were distributed in Table 11.6. For the population of employees, do the days for the highest number of absences occur with equal frequency during a 5-day work week? And we're going to hypothesis test that at a 5% significance level. Okay, so here is the observed data. When we asked the bosses, this is the information that they gave us. So you can see it's not the same amount every single day. That's the real world data. So our null and alternative hypotheses, now we should be good at these by now because we did this a significant amount in our last chapter. So the null hypothesis is that the absent days occur with equal frequency so that it's a uniform distribution. So then what would the alternate be? That they don't, right? So the absent days do not occur with equal frequency. It's unequal frequency. That is, they would not fit a uniform distribution. Remember, a uniform distribution was the one that every bar was the same height. So you got the same answer every single time, and when you graphed it in a histogram, every bar was the same height, and it just went straight across. That's what they are meaning by uniform. Okay, so here's how we're going to calculate the expected value, and then use that to come up with the chi-square. So first off, there were 5 different days of the week, and there were 60 employees in the table. You can go through here and add this up and see that this is going to give you 60 responses from the managers. So the expected value would be to take that 60 and divide it by the 5 days of the week. So we would expect that every day there would be 12 people out. All right, so here's how we're going to calculate that chi-square. All right, so first we're going to subtract the expected from the observed. All right, so we're going to do expected from the observed. So 15 minus 12 would give me 3. 12 minus 12 gives me 0. 9 minus 12 gives me negative 3. 9 minus 12 gives me negative 3. 15 minus 12 gives me positive 3. All right, then the next thing that we do is we square that value that we just got. That observed minus expected value that we just got, we're going to square that. All right, so 3 squared is 9. 0 squared is 0. Negative 3 squared, the negative gets squared as well. So negative 3 squared would be 9. Negative 3 squared is 9. Positive 3 squared is 9. All right, and then we're going to take that answer we just got and divide it by the expected value. So remember, the expected value over here was 12. So we're going to take the answer we just got, 9, and divide it by 12. 0 divided by 12. 9 divided by 12. 9 divided by 12. 9 divided by 12. Once I get these values, I'm going to add them up, and that is my chi-square test statistic. So we're going to go through and say 0.75 plus 0 plus 0.75 plus 0.75 plus 0.75, and that gives us 3. And so our chi-square test statistic is going to be 3. So if we go back to this little formula over here, you can see it's the observed value minus the expected value, that quantity squared, divided by the expected value, and then sum all of those up. That's what our sigma means. Okay, so once we figure out what our chi-square test statistic is, in this case it was 3, remember that your degrees of freedom is going to be n minus 1. So if you go back, you'll notice that we had 5 categories, right? Monday, Tuesday, Wednesday, Thursday, Friday. N was 5, so our degrees of freedom is going to be 5 minus 1, or 4. And then the way that we state the distribution for the test is this is our notation for chi-squared. And then down here, this is just that degrees of freedom. So chi-squared with the degrees of freedom. So this would be how we would state that. All right, so now I want to put that in my calculator to get a p-value. And we're going to do this the same way that we've been doing with all the other types of distributions. So we're going to go to second distribution. So the same place that we've gotten our normal and our inverse norm. Scroll down here and you'll see right here the chi-squared CDF. All right, so I'm going to choose chi-squared CDF, and it's going to ask me for my lower. That is my chi-squared test statistic right there. So I got 3, so I'm going to put that in. And then the goodness of fit test we said is almost always right-handed, and I told you that all the problems I would give you on the homework and on labs and quizzes and tests would be right-handed. So our lower value is going to be our chi-squared test statistic, and our upper value is going to be 1e to the 99. And then our degrees of freedom, as we said, is just the number of categories minus 1. All right, so when we paste that in, then the answer that it gives me is my p-value. So for this one, my p-value is going to be 0.5578. All right, so since p is 0.5578, now we're going back to the same thing that we were doing. We're going to compare p to alpha. So alpha is 0.05, 95% confidence level, so 5% level of significance. Alpha is 0.05. So since p is greater than alpha, then we decide not to reject the null hypothesis, all right? So that's that same thing that we've been doing. Now, if we decide not to reject the null hypothesis, that means we found the null hypothesis to be true. So here's how we conclude that. At the 5% level of significance, there is not sufficient evidence to conclude that the absent days do not occur with equal frequency. So we stated the level of significance, and since we failed to reject the null, we base our conclusion on the alternate, because remember, we're testing the alternate. All right, let's look at another one of those. So the claim is that there is no preference for flavor of ice cream. I could pretty much tell them the answer to that right now, but so we're going to let alpha be 0.05 again, and we're going to sample 100 people. And when we sampled them for cherry, strawberry, orange, lime, and grape, here are the responses that we got. So let's create our chi-square table. All right, now I want you to do this one on your own. I want you to pause the video and do this one on your own to make sure that you can do it, and then you can unpause it for us to fill it in. But just to make sure you get off on the right track, I want to make sure your expected value is right, okay? So your expected value, you're going to find the total number. So for us, that was 100, and we're going to divide by the number of categories. So how many categories were there? 1, 2, 3, 4, 5, right? So what's your expected value going to be? It's going to be 20. Okay, so pause the video and go ahead and fill out the rest of your table and calculate what you think your chi-square is going to be. Okay, so let's see how you did. So remember that we're going to subtract the expected from the observed. So 32 minus 20 is 12, 28 minus 20 is 8, 16 minus 20 is negative 4, 14 minus 20 is negative 6, 10 minus 20 is negative 10. Then we're going to square each of those values, right? So remember, the negative gets squared to become positive. And then we're going to divide each of those by our expected value of 20 over here. So we're going to take each of these values and divide them by 20. So now that I have these numbers, I'm going to add them all up, and that's going to give me my chi-square. So I'm going to do 7.2 plus 3.2 plus 0.8 plus 1.8 plus 5, and that gives me 18, and that is my chi-square test statistic. So now I'm ready to throw that into my calculator. My degrees of freedom are going to be the number of categories minus 1. So again, remember there were 5 categories here, right? So it's going to be 5 minus 1 for my degrees of freedom. And again, I would state that distribution the exact same way. So to get my p-value, I'm going to go back to distribution, go down to chi-squared CDF. I'm going to put in the chi-square test statistic we got for the lower value. That was 18. It's almost always right-tailed, and for us it's always going to be, so 1e to the 99, and then degrees of freedom was 4. So that gives us 0.0012. All right, so since p is 0.0012, since that's less than our alpha value of 0.05, then we're going to decide to reject the null hypothesis. We're going to look at one more test in our next video for chi-square, and that is the test of independence.